All right, guys, so welcome to episode 4. It has been a while since I posted a video, so I'm excited to post this one that is going to introduce our new chapter. So today's episode is going to be on section 5.1, so starting chapter 5, lesson 1. So what we're going to learn in this episode is we're going to talk about rational numbers. We're going to talk about what those actually are and how to determine if a number is a rational number. Then we're going to talk about how whole numbers, integers, and rational numbers are related. We've talked about whole numbers and integers in class, and now we're going to tie those in with rational numbers. Next, we're going to talk about terminating decimals versus repeating decimals, and then we're going to figure out how to know if something is a terminating or a repeating decimal. So we're going to start with some key vocabulary. So the first thing that we're going to talk about is what a rational number is. So a rational number is a number that can be written as a fraction. So ignore the picture at the bottom for now. I'm going to talk about it in a second, but I want to first talk about rational numbers. So if I want to think about a number that can be written as a fraction, let's think about some examples. So if I think about a number that can be written as a fraction, right? Well, obviously fractions can be written as fractions, right? So 1/2 would clearly be a rational number, right? Because that can be written as a fraction. Well, what about the number 2? Can I write 2 as a fraction? Because right now it's just a whole number. So if I think about 2, I can actually write that as a fraction with a denominator of 1. So 2 is a rational number because it can be written as a fraction. Well, what about the number -3? Can -3 be written as a fraction? It's going to be similar to what we did previously with 2, and that -3 is just going to be the same as -3/1. So yes, that is a rational number. What about a decimal? So what about 2.5? Can I write 2.5 as a fraction? Well, yeah, I can write it as a mixed number. 2.5 tells me that I have 2 wholes, and then this 0.5 tells me that I have 5/10. This would also be equal to 2 1/2. So those are some examples of rational numbers. So then if we think about whole numbers and integers, which we've talked about in class, whole numbers and integers are going to be rational numbers. Just like the previous examples that we did, we used 2 and -3 as examples. We can write those as fractions. So just a quick reminder of why whole numbers and integers are rational numbers. Remember that a whole number is counting numbers greater than 0. So 1, 2, 3, 4, 5, 6, going all the way to infinity. So they're going to be counting numbers greater than 0 and not including 0. Integers are similar to whole numbers, except they also include negative whole numbers. So it can be -1, -2, -3, so on and so forth. So whole numbers and integers can be written as fractions. So now I want us to look at this picture below here. And we're going to talk about what this picture actually means. So thinking about this picture here, we are going to talk about some examples, these questions here, to figure out which numbers fit into which section. So what I'm going to do first is I'm going to redraw this picture. And when I redraw this picture, I'm going to start with the smallest circle. So the circle that was in the middle of that picture, the smallest circle is whole numbers. The reason why this circle is the smallest is because whole numbers make up a really small part of all the numbers, right? Whole numbers are only counting numbers greater than 0. So that'll include 1, 2, 3, all the way to infinity, I guess. I don't know if infinity is a whole number, but we could say like 1,000 or something. So 1,000 will be a whole number, right? So our first circle is whole numbers. Then we have a second circle that's a little bit bigger than whole numbers, and that second circle is labeled with integers. Whole numbers are inside of integers because whole numbers are integers, right? Integers are positive and negative whole numbers. So whole numbers are the positive part, then the negative whole numbers, so for example, -3, -5, -1,000, those are going to be integers because they are negative whole numbers. So integers is going to include a little bit more numbers, right? Because it includes positive and negative whole numbers. And then the biggest circle that includes both integers and whole numbers is going to be rational numbers. Rational numbers, remember, are numbers that can be written as fractions. So 2 would be a rational number, which is included in whole numbers and integers. -5 will be a rational number because it is a negative whole number. I could also include 1/2. And 1/2 is in this bigger circle, but it's not going to be included in these smaller ones, right? Because 1/2 is not a whole number. We could have a decimal of 2.5, right? The list goes on and on and on. So just keep in your mind that whole numbers is the smallest circle because it has the least amount of numbers. Then integers has a little bit more, and then rational numbers is going to include a lot of numbers. Some examples of something that's not a rational number: pi would not be a rational number, so it is outside of this circle. The reason why pi is not a rational number is we can't write it as a fraction, right? If we're writing it as a decimal, it's 3.14, blah, blah, blah. I'm sure some of y'all know all of the some of the digits of it, but these numbers keep repeating forever and there's no pattern involved. So pi would be an example of a number that is irrational. And we talked about this in class, that 0 to the power of 0, right? We don't know what that is. That's called an irrational number because it is not defined. It doesn't have a value. And then also anything that has a denominator of 0, right? I can't do 3 divided by 0. That would be an example of an irrational number. So there aren't as many of these, but just keep in mind that not every number can be written as a fraction. So that was the example there, kind of explaining what that circle is. So let's use this circle to answer some of these questions. So the first question says, are all whole numbers rational numbers? So if I think about this small circle here, are whole numbers rational numbers? Well, yes, all of these numbers can be written as a fraction. So the first answer is yes. Second question, are all integers rational numbers? So if we think about integers, integers are the next biggest section, and those are positive and negative whole numbers. All of these numbers can be written as a fraction. So that means that yes, all integers are rational numbers. Third question, are all integers whole numbers? Are all integers whole numbers? So if we think of some examples of integers, -3 is an example. So is -3 a whole number? No, because it's less than 0. So we thought of an example of an integer that is not a whole number. Some integers will be whole numbers, right? If I think about integers can be positive whole numbers, so like 1 would be an example of an integer that's a whole number, but not all of them. That keyword all tells me, nope, not all of them. Last question, are all rational numbers integers? Are all rational numbers integers? Well, if we look at some of these examples, 2 is an integer, so that works. -5 is an integer. Is 1/2 an integer? No, because it's a fraction, right? It's not a whole number. So are all rational numbers integers? We're going to say no, that is not true. Okay, so last slide here is on terminating and repeating decimals. So the definition of a terminating decimal is a decimal that ends. It ends because when you divide, you get a remainder of 0. So a terminating decimal ends because when you do the division, turning the fraction into a decimal, it's going to have a remainder of 0. And then a repeating decimal never ends. That means it's going to go on forever and ever and ever, right? So it never ends. So it is a digit or a group of digits. So sometimes it's just one number that repeats, and then sometimes it's a group of numbers that repeats without end. So the question is here is to figure out, how do I know if something is a terminating decimal or a repeating decimal? So we're going to go through a couple of examples together. So the first example is 3/8. And this is what we're going to do in class on Wednesday or Thursday, depending on when you have math class. So our first example is 3/8. And my question is I want to determine, is this a repeating or terminating decimal? So the way I'm going to figure that out is I need to write 3/8 as a decimal. So when I think about my denominator of 8, I think, okay, does that scale up to 10? The reason why having a denominator of 10 is helpful is because, for example, if I have 2/10, that means that I can write my decimal super quickly as 0.2 because my 2 is in the tenths place. 8 does not scale up to 10 evenly, so this is not going to work. Then I think, okay, can I scale it up to 100? Because if I think about 2 over 100, that means I have 2/100ths, which means I have a 2 in the hundredths place, right? So if I can get a denominator of 100, it's really easy to write the decimal, but 8 does not scale up to 100. 8 does, however, scale up to 1,000. So if I think about having 2 thousandths, that means I have a 2 in the thousandths place, so that means that I would have 0.002. So if I think about 8 scaling up to 1,000, for those of you that know this, cool. Not, then I'll show y'all how else we can do 3/8. But if we know that 8 goes into 1,000, it goes in 125 times. So I can multiply 8 by 125 to get to 1,000. Since I'm scaling up, I need to do the same thing to the numerator and the denominator to have an equivalent fraction. So 3 times 125 is going to be 375 thousandths. So if I want to write 375 thousandths as a decimal, that means I'm going to have 0.375. So thinking about this decimal, is that a repeating decimal, which means it ends, or is that is that a terminating decimal, which means it ends, or a repeating decimal that means it is going to repeat forever and ever? Well, this is an example of a terminating decimal because it ends with a digit of 5, right? 375 divided by 1,000 would have a remainder of 0 because I can write my decimal and it does not repeat. So this is a terminating decimal because it ends with the thousandths place. If you did not know about scaling up 3/8 to 375 thousandths, something else that you can do to change this fraction to a decimal is you can actually divide. So I can do 3 divided by 8. 8 will not go into 3, so I'll say that's going to be a 0. To keep dividing, I'm going to add my decimal and my zeros. So then 8 goes into 30 3 times. 8 times 3 is 24. I subtract and get 6. Bring down my 0. 8 goes into 60 7 times. 8 times 7 is 56. I subtract and get 4 and bring down my 0. 8 goes into 40 5 times. 8 times 5 is 40. Subtract and get a remainder of 0, which tells me this is a terminating decimal. Okay, so that is our first example. Second example is if I have the fraction 5 over 11. When I think about the number 11, I know that that is not going to be able to scale up to 10, 100, or 1,000. So the only strategy that I'm going to have here is to divide. And we're going to talk about in class different strategies besides dividing and scaling up to 10, 100, or 1,000 that we can use to change it to a decimal. But just for this episode, I'm going to show these two strategies. So again, I'm doing 5 divided by 11. 11 will not go into 5, so I have my 0. And then to continue dividing, I add my decimal point and my zeros after. 11 goes into 54 times. 11 times 4 is 44. Subtract and get 6. 11 goes into 65 times. 11 times 5 is 55. So I bring down my 0. 11 goes into 54 times. 11 times 4 is 44. Bring down my next 0. 11 goes into 65 times. And if you notice, we have a pattern developing of 4, 5, 4, 5. So this is going to be an example of a repeating decimal because I'm going to continue to have a remainder. I'm never going to have a remainder of 0. So this fraction is a repeating decimal. And the way that we would write the repeating decimal is we write the 0.45 with this fancy bar on top, which tells me that 45 is going to repeat forever and ever and ever. All right, guys.